Say I have this compound. Okay? And I give you Ksp for this compound. It's 4. Is this less than 1 or greater than 1? Is it going to be less than 1? Not the number 4 I need. But the Ksp value. A little less than 1 or a lot less than 1? A lot, crazy lot. And this one is ridiculous. Okay? So it's insoluble. And let's say I wanted the molar solubility of this. Okay? So I'm asking for the molar solubility. What would you do? You would say, okay, Fe, you write down the reaction. And we expect you to be able to write this reaction. Okay, there's the reaction you should be able to write down. And you solve it with the ice table. Okay, we'll change colors here for a moment. Ignore the solid, 0, and 0. Then you shift to the right, so plus x, and plus, what do I write here? 3x, because of that 3 right there. And so x and 3x. So what you're going to get is Ksp, which is 4 times 10 to the minus 38. Equals x times 3x cubed. What is that? 27 x to the 4th. Hey, can somebody find x for me? By the way, this would be the molar solubility. Okay? And we're expecting this to what? Be a large number or a small number? Small number, why? It's not very soluble. K is small, so we're expecting this to be small. Okay, and I'll get another page out here.
Question?
Yeah.
Are we ever going to have to do anything with activities in Ksp values at all?
Activities, not on this final, no. But you should have seen it in your last lab. So in our class, that's the one place you should have seen it. Okay. What was I up to? Oh, what's this number? Okay, 2 times 10 to the minus 10. Okay, I'll trust you. Did you just make up a number? That's cool. So not very soluble, it's a small number. Now, I'm going to add to this solution KCN, and I'm going to have it be 6 molar. Okay? And I'm going to give you, you think randomly, a Kf value. Kf, oh my gosh, 1 time, oh, Kf, large number, small number? So it's bigger than 1, a lot bigger than 1, or a little? A crazy lot, and this one is ridiculous, donkulous. 1 times 10 to the 42. And then the compound is C. Okay. So now, there's kind of 2 things we can do with this. Let me just ask you because I'm not sure. This is going to lead us to a mixed K problem. But before we get there, just look at the right-hand side. If I asked you, hey, find the equilibrium concentrations of, say, the iron 3+ in this problem. Do you need me to do that? Or are you cool with that? Fine. So if I asked you, looking only at the right-hand side, find this value.
Do it.
Need help? Don't need help?
Need help.
Do it. Raise your hand if you need. Okay, okay. Let's do that. Ignore the left-hand side just for a moment. Okay, so you should be able to write the reaction for this. Make sure you can do that by the final. You don't have to do it now. You have a couple days to learn it. Okay. There we go. So you should be able to write that kind of reaction. And then if you needed it remember, an equilibrium, concentration, pressure, whatever, use ice table. Okay, so I would actually have to give us a number here. Let's say I'll write it in brown for given. Let's say this is 2 molar. I don't know. Okay, and 0, 0. So let's say what's in brown is given. All right, so you need those concentrations, and then you just do an ice table. So it's going to shift back to the left. So minus x plus what? 6x, because there's 6 there, and plus x. This would be x, 6x, and minus x. So Kf, did I mess up something? Oh, 2, thank you. 1 times 10 to the 42 equals 2 minus x over x times, this is funny, 6x to the 6th power. Okay, whatever. Oh, in this case, is x large or small? Okay, let's think about this. Equilibrium lies on which side? What side is favored, right or left?
Left.
The right, how did you know that?
Oh, just like
Because K is gigantuous, whatever, okay? So, because K is so big, equilibrium lies on the right like crazy. So, would you expect it to shift to the left at all? Not really. It will, but barely. So, I'd expect X to be super tiny. Okay, if you don't know this, I'm the reader here. I'm going to go to the end of chapter 17 right now is where I'm flipping. Just as you need to review this later. Okay. Oh, I guess somebody thinks I should write which there. Whatever. Okay. Which, what, whatever, x values are small. All of these. So Kf. Okay? Kf. So know that, that's page 112. Page 112. Okay, so I would expect this x to be gone, and then you don't need, this is something you can do on your calculator. Alright, can we, now you know how to get that, that would just be x. Is that okay? Yes. Would you have to justify your assumption? If you did, you just get to x, and you're going to compare it to the number 2. So you go x divided by 2 times 100. If that's less than 5%, you're good. This should be crazy, crazy tiny. Yeah.
Question?
Yes.
How do you decide which side is the product and which side is the reactant?
How do you decide what side is the product, what side is the reactant? The formation of a complex ion is always written like this, where the complex ion is always on the right. It looks a little bit the opposite of a solubility product reaction, where the solid is always on the left. You always write it in that template. Now, technically, we don't have to do that. That's just our common, what would you call that?
Procedure.
The only word that comes to my mind is style. I don't know. Convention, thank you. That's our common convention. Okay. All right, can we go back to the blue problem now? Okay. Now, let's say I had KCN to the previous problem, which was the iron oxide, the iron 3 oxide. What do you do? Well, what you do is when I add KCN, what do you think about K when you think about K? Yeah, ignore it. Spectator on. CN, now look over here. Which one of these 3, I'll go 1, 2, 3, do you think it'll react with?
2.
2. The second one. There's two reasons why you might have thought that. Can anybody give me one of those reasons? The charge is 1. Yeah, Cn is minus, so it has to react with a plus. Anybody know the second possible reason why you might think that? Well, because I gave you this molecule here. Iron and Cn never go together, right? Okay, so for either of those two reasons, you would say, well, that iron is going to react with the Cn I'm adding to the problem to form FeCN6 3 minus, and there's 6 of those. Okay? So I know I have a combo reaction where this is a KSP and this is a KF. I call this in my reader a mixed K problem because there's 2 Ks involved. Okay? So how do you do this problem? Well, you do an ice table. But before you do the ice table, you need the new reaction. So you want to add these 2 up and cancel what cancels on both sides. And I did one of these in class. It was the photography problem that I did 2 classes ago. Okay? Now, before I continue solving the problem, when I'm adding Cn to this solution, am I expecting the molar solubility to go up or down? Up. Why? Yes, Le Chatelier's principle. I'm removing this, so this top reaction must shift right to restore equilibrium. So if it moves right, it's becoming more soluble because I'm getting rid of solid. So the molar solubility better go up numerically. All right, this is my new reaction. So let's go to the next page here. Okay, ice table. Ignore solid, Cn. What number? Now I gave you 6 molar, but what number do I put here? This is tricky for some people. Do I put 6 here? Yes. You took that a lot worse than I thought you would. Why don't you want 6 there?
Because you brought it up.
You don't want 6 there because of this 6?
Yeah.
Yeah, this 6 in the I line, remember the I line is as is. The stoichiometry does not happen in the I line. And so these coefficients do not affect it. Okay, so the coefficients do not affect the I line at all. Whatever number you're given goes in as is. The C line, totally different. The C line is affected by the coefficients. Okay, one thing I need to do before I continue on, I need to know the K for the new reaction. So K for the new reaction is KSP. Am I going to add KSP and KF or multiply?
Multiply.
Okay, good. I need that number. So it's 3 times 10 to the minus whatever. No, 4 times 10 to the minus 38 times 10 to the 42. What is that number? Yes, it's a 3. Oh, no, 4 times 10 to the positive 4. Am I by myself here? Is anybody still here? It was 4 times 10 to the minus 38 times 1 times 10 to the 42. Does that not happen for everybody? You got 3? Okay. All right. Okay. So, can I continue with the problem as is? Okay. Why do I multiply those? Because I added the reactions. When you add add the reaction, you multiply the K's. If there were delta H's, you would add them. But these are K's. Okay, can I continue with the reaction as is? Wait, what? Oh my, I did that in my head. Someone got that? You better yik yak that right now. I'm checking yik yak right now. Okay. All right, can I continue with the problem as is? Now, if no, why not? I need what? A 0 where? On the unfavored side. Do I have that? What's the favored side, right or left? The right, and I don't have a 0 on the left. I can't continue. Everybody got that? No. Do I need to say that again? Okay. Remember the rule? I need a 0 on the unfavored side. Does that sound vaguely familiar? Oh my gosh. Okay. That's okay. It's not the final yet. We still have hope. Okay. Let me refer you to a page. Oh my gosh. This is chapter 16 I'm moving to. Page 84. The main concept, there must be at least one 0 on the unfavored side. Okay, apparently I need to fix that. But does this sound familiar? We did this with buffers. This course is a stoichiometry problem. Does this ring a bell to anybody? Okay. So I always must ask that, especially, really all the time. It's good to ask this question. But this pops up all the time in titrations, acid-base stuff, buffers especially, and it pops up in KF and KSP problems pretty often. That was page 84 at the top. Okay, so the favored side is which one, right or left? According to K, it's the right because this is large. Zoom out a little bit. So I need a 0 on the left-hand side. I don't have one right now. So I'm going to put a little space here. How do you get a 0? Because I'm at a constant, because the volume's not changing, I can just assume these are also moles. And go minus. Oh wow, I picked kind of a tough problem. Okay.
You've done it. 6.
Oh gosh, I'm trying to consider whether to continue with this problem. It's just tough. Do you want to, is this too depressing? Should I stop this problem? Who wants to stop? Is it going to be on the final? Okay, let me just set it up for the folios who want to see it. Okay, you can zone out later. Okay, because of the subtraction, I have to 6 times 1 to subtract 6 here to get 0. And so I'm adding 1 here and adding, what do I add here? Yeah, 1 times 3. This is 3, and this is 1. And this is now my I line of the ice table. I would go C and E. Don't worry, folios, you want to stop this. Plus, so I shift back to the left, plus 6x minus x and minus 3x. So this would be 6x, 1 minus x, and 3 minus 3x. I would set up my K expression. Would I assume x is small? It's remember, shifting away from the favored side. I definitely would. Yeah, shifting away from the, you don't have to, but it makes your calculation easier. Shifting away from the favored side, and because of that, x is going to be small. Whenever you shift away from the favored side with x will be small. And that's really common in a KSP problem, and KF problems, and mixed K problems. Yeah. this, this, because I have to subtract all of this. But remember, there's three places where the coefficient appears. The C line, the exponent of the K expression, and right here, the stoichiometric part of the problem. So I have to subtract 6, but it has to be a factor of 6. So then it must be 1 times 6. In the same way I'm adding 1 here and 1 times 3 here. Yeah. I can't subtract 6 here. I mean, I can, but I have to realize it's times 1. Because there has to be 6 of them. Because of that 6. Okay, chew on that for a while. Okay. Alright, I'm going to pause that. That was a mixed K problem. The easier one was the one I did in the last class, though. Yes? No, to the reactant. He asked, are we shifting to the products? No, to the reactants, because we have a 0 on the unfavored side. So you're always shifting towards the unfavored side. Because I need it, because there's a 0 here. Why do we create a 0? Because we need a 0 on the unfavored side. Okay, I'm going to pause.